the first talk today in this webinar series of the upper atmosphere is Ionosphere introduction and formation. So we will first give a brief background about the upper atmosphere. Yeah, the Earth's upper atmosphere is the height region in the atmosphere from about 100 kilometers to about 1000 kilometers. Below that, we have the lower atmosphere, which extends from about the middle atmosphere, which extends from about 10 to 100 kilometers. And the region below 10 kilometers is known as the lower atmosphere. So these boundaries are not just artificial or arbitrary boundaries. They are governed by physical processes which take place in these different regions. For example, the boundary at 100 kilometers signifies the height where a transition from an atmosphere which is well mixed by the process of turbulence or eddy diffusion to a diffusively separated atmosphere by the process of molecular diffusion occurs. So hence this boundary at about 100 kilometers is also known as the turbo pause, where the turbulence stops. Now, below the turbo pause, the atmosphere has a uniform composition and therefore it is called the homosphere. And above the turbo pause, the composition varies with height or it is heterogeneous and therefore it is called heterosphere. Now, the upper atmosphere consists of two major parts. One is the neutral atmosphere, which is the major part, and an ionized minor part, which is called the ionosphere. So the ionized part is very small in concentration, but even then, at the peak of the ionization, which occurs at about 300 to 350 kilometer altitude, the ionization is only about 1/1000th of the neutral density there. So therefore, that gives an idea of how weak the ionization is compared to the neutral part of the atmosphere. Hence, the ionosphere is defined as a weakly ionized plasma. The main property of the plasma is it contains a sufficient number of free electrons and an equal number of positive ions and a large background of neutrals. So this criteria is satisfied in the upper atmosphere where we have the ionized plasma or the ionosphere. So though it is very minor, it is important to note that it plays a very important role in radio communication. Most of the communication in the world is through radio waves, which is a part of the electromagnetic wave spectrum. Now, as you can see from the inset diagram here, the height region above about 85 kilometers is marked as a thermosphere, and the dashed graph shows how the electron density or the concentration of electrons in this region varies with respect to height. So this represents basically the ionosphere, and this part, because of its very high and constant temperature, which is of the order of 1200 to 2000 Kelvin, is called the thermosphere. So we have the thermosphere and ionosphere, which refer to the same height region of the atmosphere, but the former refers to the ionized minor part and the latter to the neutral major part. Just a moment, I will get my pointer on so that you can see things better. Okay, so the thermosphere and ionosphere exist at the same height range from about 85 kilometers to about 600 kilometers and more. And the region below 85 kilometers is classified as mesosphere, stratosphere, troposphere, etc., depending upon the variation of the temperature with respect to height. these regions you may have heard of while studying about the neutral atmosphere. So now we we see how the ionosphere is produced, and for that the main agency or the main ionizing source is the solar rays, the radiation from the sun at short wavelengths, as marked here in the figure. These are all electromagnetic waves, part of the electromagnetic spectrum. The X-rays, which are having shortest wavelength less than about 10 nanometer. Then the extreme ultraviolet between 10 to 120 nanometer wavelengths. Then far UV, then middle UV, near UV, etc. And then we have the visible and infrared radiation coming from the sun, which we can see as the visible light. So all these radiations have different roles in the atmosphere, and some of them penetrate down to the earth, for example, the visible and infrared, whereas some other radiations are absorbed either in the stratosphere or mesosphere or even thermosphere. And because of that, they produce different effects there. So because of the interaction of the neutral atmospheric constituents with these radiations, the process of photoionization takes place, and that is the mechanism of production of the ionosphere. Now, the left panel shows the temperature structure in a bit more detail, particularly in the thermosphere, where the point here to see is that the temperature structure is different during solar minimum and solar maximum. The temperature is much higher during solar maximum. That's an effect of the solar activity. And this panel here shows how the electron number density of the free electrons produced by the photoionization process, marked by E, and the red line graph shows how it varies with respect to height. And also the other graphs show how the neutral constituents like the molecular oxygen O2, molecular nitrogen N2, and the atomic oxygen O varies with respect to height. So as we said earlier about the homosphere and heterosphere, this graph also shows that up to about 100 kilometer height, all the graphs are merging each other and having the same slope. And so that means the composition is uniform there. And above that, each graph is separated. That means the composition varies with respect to height. One more point here to note is that the height variation of atomic oxygen is somewhat different from that of the molecular constituent. This is because, as written here, the N2 and O2 are primary constituents of the atmosphere, whereas the atomic oxygen is not a primary constituent, but it is produced by photo dissociation of the O2 molecule. That means the O2 molecule absorbs some energy from the solar radiation of suitable wavelength, and it breaks up into two oxygen atoms. So that is how oxygen atom is produced. Therefore, its profile is different from that of the other molecular constituents. Now, this graph also shows what is called the Iyer cooling. So some of the atmospheric constituents, they radiate in the infrared and thereby leads to cooling of the atmosphere. Whenever radiation is absorbed, and that region gets heated up, and when it is radiated out, that leads to cooling. Okay. Yeah. Now, once again, we go to that boundary at 100 kilometer, which has other physical significances, which is also known as the Karman line, below which most of the atmosphere, 99.99997% by mass, stays below 100 kilometers. So we can say almost practically all atmosphere exists below the Karman line. Now, so above the Karman line, though the atmosphere is practically very, very little, there are many interesting events, phenomena taking place there. For example, we all know about the northern lights or the aurora taking place at the polar regions. So they are spectacular geophysical displays which occur at the height of about 150 kilometers, as shown here. Similarly, the meteors, they are visitors to the solar system. They occasionally, during a part of their orbit, get enter into the solar system, and then they burn and they begin to glow somewhere at heights of about 100 kilometers. But some heavier ones will not be completely burned up, but will come further and they sometimes hit even the surface of the earth as meteorites. So that is the meteors is a phenomenon taking place in this region. Then other the whatever the different layers of the ionosphere we are going to study now, going to talk about, they also exist in the region above the 100 kilometer. Here it is marked. There is a slight mistake here. The lower one, this is ionospheric D layer. Above that you have the ionospheric E layer, and then much above you have the ionospheric F layer. All these are existing in this height range. Now, also technological systems like the space shuttle, the International Space Station and the space shuttle, they orbit at altitudes of about 350 to 400 kilometers, which is in the F region of the ionosphere. Similarly, many satellites are used for upper atmospheric studies or for communication or for remote sensing, etc. They have to close to this region, or some of them even operate their orbits pass through this region, and then they experience what is called a significant atmospheric drag, which is a very important factor which affects the lifetime of the satellite. So these regions have many importance in not only physics or science, but also technological applications. Now let us see how the ionosphere is defined. A classical definition of ionosphere will be like this: is defined as that part of the upper atmosphere containing sufficient number of free electrons and ions to affect the propagation of radio waves. So the main emphasis was how the ionosphere is affecting propagation of radio waves, or in other words, radio communication. So we said electrons and ions are produced by photoionization process. So if their number is sufficient to affect radio propagation, that region is defined as the ionosphere. So if you give a practical definition in terms of the number of ion and electron pairs per unit volume. So if you say, if we define ionosphere as having greater than a few hundred particles, including ions and electrons per centimeter cube, then the ionosphere exists around 7 out of the 9 planets of our solar system. So it's not only for Earth, but also other planets who have. I put a question mark at 9 because of the recent classification of Pluto as a small object or a dwarf object, and declassification from a planetary status. So yeah, that's not a point for us. But even then, even in Pluto, electron density of the order of 1,000 per centimeter cube have been estimated, not really measured, but estimated. So thus leaves only Mercury as the only planet without an ionosphere. So all other planets in the solar system have ionosphere. And not only planets, ionospheres have also been observed around 6 of the moons of the giant planets. As we have the moon as a satellite of Earth, the other satellites, other planets have their own satellites. For example, the Io, Callisto, Europa, Ganymede, these are the major satellites of Jupiter, and ionospheres have been found around them. Similarly, the satellite of Saturn, Titan, has also ionosphere. Then satellite of Neptune, Triton, also has ionosphere. Thus, we have totally 7 planetary and 6 satellite ionospheres. So total 13 non-permanent ionospheres. They are always there. Always there. Neutral atmosphere is there. Always solar radiation is coming. So they are always produced. But in addition to this permanent ionosphere, there are some transient ionospheres around comets during their short residence inside the solar system. So the cometary head gets ionized and you get an ionized region around the comet. And such an ionosphere was detected around the comet Halley by the cometary mission GO2. So ionosphere is not exclusive to Earth, but it has its presence in other parts of the solar system also. Now, how the existence of the ionosphere was inferred. It goes back to the geomagnetic history. So the existence of ionized or a conducting region in the upper atmosphere was first inferred from the geomagnetic field measurements of Balfour Stewart in the year 1882. So an example of similar to what he saw in the magnetic field variations is shown here. The graph shows the recording of the geomagnetic elements. The geomagnetic field is a vector quantity. It can be resolved into a horizontal component H, a vertical component D, and a declination angle D. So we at low latitudes, the important component is the horizontal component H. So this is recorded at the Alibag Indian Magnetic Observatory at low latitude station near Bombay. So if you look at this graph here, y-axis is the strength of the magnetic field and the x-axis is the universal time. So the local time here in India is 5.5 hours ahead of the universal time. So we see here that the magnetic field increases during the course of the day and reaches a maximum at about 11:30 in the noon time, and then it starts decreasing and remains almost steady throughout the night. Again, next when sunrise comes, they start increasing. So Balfour Stewart found in 1882 this kind of magnetic field variation, and then he proposed that there must be some conducting layer, a current carrying layer somewhere in the heights, upper atmosphere, through which when a current passes, it generates its own magnetic field, and this magnetic field is superposed on the Earth's main magnetic field, and that is the reason for this kind of diurnal or daily variation of the magnetic field. So it was inferred like that from the geomagnetic observations. Now, I try to illustrate this a bit more clearly. This is a geomagnetic field observation, X component, horizontal component from our Indian equatorial station, Tirunelveli. So here, the actual increase during the course of the day, that is the actual value at a given time t minus the nighttime value, is represented as delta H and plotted on the y-axis, and the x-axis is in the Indian Standard Time. So the two graphs, one is for April 2007, the red line, which is a solar minimum period, and the black curve, April 2001, is for the same month, but for a solar maximum period. So we see a clear difference between solar maximum and solar minimum in the variation of the graph. And we see here that around 11 to 12 noon time, the magnetic field attains a maximum value. So this clearly shows that there is a very strong solar control on the variation of the magnetic field, and this solar control is through the production of the ionosphere and the ionized layers and the currents flowing through them. So there is also another parallel development to infer about the existence of the ionosphere. That is like this. We all know that the well-known scientist James Clerk Maxwell, he postulated the electromagnetic theory and also electromagnetic waves for explaining the light and other sorts of other kinds of wave motions. So in 1865, he proposed electromagnetic waves. And then in the year 1887, a German scientist by name Hertz, he experimentally produced actually electromagnetic waves by his famous experiment. And coming further in time, in 1895, an Indian scientist by name J.C. Bose, he gave his first public demonstration of electromagnetic waves at the invitation of the Royal Society, London. So the picture shows Sir J.C. Bose with his apparatus for producing electromagnetic waves. He was working mainly on the microwave region of the electromagnetic spectrum. Then further, in the year 1901, a very hallmark development took place. That is, the Italian scientist Marconi, he succeeded in generating electromagnetic waves, radio waves, and propagating it over a large distance across the Atlantic Ocean. So he transmitted radio waves across the Atlantic Ocean on December 12, 1901, using the instrument which was devised by Sir J.C. Bose. So this became a new turning point, and then the people started to thinking how these radio waves propagate over such a long distance. So those days, the communication was so weak that the geomagnetic history of Balfour Stewart's explanation for the magnetic field variation due to conducting layer, etc., was not known outside the community of geomagneticians. So therefore, to explain the Marconi's success, an overhead conducting layer was invoked anew by Kennelly and Heaviside, both independently, in the year 1902. So they said that there is again a conducting layer, and this layer is reflecting the radio waves transmitted by Marconi. And so this is again only a proposition, but actually later in the year 1925, two British scientists, Appleton and Barnett, they made an instrument, an equipment to transmit radio wave in the vertical direction and get it reflected from that conducting layer. And they could in fact even measure the height of that layer as about 100 kilometers. And since it is a sort of conducting or electrified layer, they called it the E layer. So any further layers discovered above that used to be called F layer, and below that used to be called D layer. So this is the conclusive experimental evidence of the existence of an ionized or conducting layer at the upper atmosphere. So this illustrates how Marconi's radio waves would have traveled from the transmitter, shortwave transmitter. That is, shortwave means frequency between 3 and 30 megahertz, or wavelengths between 100 and 10 meters. So this is the transmitter here. So the radio wave was sent upward at an angle. So here some conducting layer might have been there, which was later called ionosphere. So the wave got reflected from there and came back to the ground, and the Earth's surface is also a good conductor. So it's again reflected back to the ionosphere, and again, so like that by multiple hops, radio waves could travel over a long distance from the transmitter to the receiver, overcoming the curvature of the Earth. So this is what might have happened in Marconi's experiment. So later on, this radio waves and its propagation over long distances has been very profitably used for radio wave communication using the ionosphere as the medium. So as shown here, the ionosphere is here by this light pink color. There is a transmitter here, and then there are different frequency ranges or wavelength ranges of radio waves. In general, radio waves are from about 30 kilohertz frequency to about 300 megahertz. But different wavelength regions are named differently, like very the low frequencies, which are lower in the frequency. Then you have what is called high frequency, and then we have called very high frequency. So the different types of waves propagate through the ionosphere in different ways, and all of them are very successfully used for communication. Some of the waves, like the very high frequencies, they do not get reflected from the ionosphere. Therefore, they pass through the ionosphere, but then so they cannot be used for this kind of a communication mode. but we can take advantage of that phenomena by having a satellite at much higher heights, at about 1,000 kilometers or more, and the radio waves from the ground transmitter can go up to the satellite. Then satellite can receive it and retransmit towards the receiver. So that is the basic principle of satellite communication. So for all these different types of communication uh, in the radio wave spectrum, the ionosphere has been very profitably used in subsequent years, and that was the main interest in the study of the ionosphere. This illustrates a bit more clearly how the HF high frequency 3 to 30 megahertz range travels from the transmitter to the receiver. So as the angle of transmission is changed, some of them pass through the ionosphere, some of them get reflected from different heights and reach different ranges, different distances. So we can communicate over all this area by using transmission at different angles. However, there's a minimum distance called the skip zone here, into which no reflected wave from the ionosphere reaches. Therefore, communication over this range cannot be established by this mode, and therefore that region is called the skips. You have to skip that much distance for HF communication. So this is all by way of introduction of the ionosphere, and now we go a little bit into some theoretical aspects of how the ionosphere is produced. So it's a very celebrated scientist, Sidney Chapman, who first proposed the theory of photoionization way back in the year 1931. So let us see what is the physical process in photoionization. So the production of an ion electron pair from a neutral atom by absorption of a photon coming from the sun or from any other source of suitable energy. So the suitable is very important, because depending upon the atomic structure, the energy by which the electron is bound to the atom, certain minimum energy is required to knock it out or to remove it from the atomic structure and make it a free electron. So if you give energy, if the photon has energy more than that minimum energy required, then it will be able to knock out an electron and produce a free electron. And once the free electron has gone, electron has been freed, the remaining atom gets positively charged, has a positive charge, and so that becomes a positive ion. So this is how the photoionization process works. So to give some mathematical aspects of it, Chapman made some simplifying assumptions. He assumed the atmosphere is exponential, which we know. The atmosphere parameters like density, pressure, etc., they decrease exponentially with respect to height. That is why, as we mentioned in the first slide, at about 100 kilometers, most of the atmosphere stops because of this exponential variation, but it doesn't become zero. That is also a property of the exponential variation. So the rate of exponential variation is governed by a constant called scale height, capital H, and it is related to the Boltzmann constant K, the temperature, the mass of the atmospheric constituent, and the acceleration due to gravity. So this decides the rate, how fast or how slow it varies with respect to height. Then another assumption he made is that the atmosphere is plain horizontal stratification. That means there are different horizontal layers. The properties of the layer do not change much in the horizontal direction, but in the vertical direction, they change. That is the meaning of horizontal stratification. And by plane means the Earth's curvature is neglected. Then he assumed that the absorption of solar radiation is proportional to the number density of the gas particles, which is true. If there are more gas particles, more amount of energy will be absorbed from the solar radiation. And then he assumed constant absorption cross-section. That will be true if the radiation coming is monochromatic and if there is only a single absorbing component in the atmosphere. So this is not actually true, because we now know that there are many radiations, as we showed in the first slide. that there are many radiation far UV, near UV, etc. coming from the sun. So it is not monochromatic, and we know in the atmosphere there are nitrogen, oxygen, and other constituents. So it is not a single component. So that will add to some complication, but nevertheless, the basic properties of the ionosphere can be explained by this theory. Now, the primary photochemical reaction that produce the ionization are like this. One kind of reaction is photodissociation. We mentioned the O2 molecule absorbs a certain wavelength, which should be less than 242 nanometer, depending upon the molecular structure of this. And then taking this energy, it breaks up into two oxygen atoms. So the condition is the Hc over lambda, that is the energy, should be more than the dissociation energy, which is 5.12 electron volt for the oxygen molecule. So this is just an example. Similarly, many other constituents can also be photodissociated, and then the atom can be split up into atoms. Now, the photoionization is another process. So, for example, the atomic oxygen that is produced in this process absorbs a certain wavelength satisfying some criteria, that it should be less than 91 nanometer for atomic oxygen, and then it gets converted to a plus ion, positive ion, and a free electron. So the table here shows what is the ionization potential or the corresponding wavelength required. So if you look at atomic oxygen, its ionization potential is 13.61 electron volts, or the corresponding wavelength which decides this limit is 911 angstrom unit, but that is equal to 91.1 nanometer. So that is why this limit comes here. Similarly, nitrogen molecule can be ionized to get a N2 plus ion and a free electron. Oxygen molecule can be ionized to get O2 plus and ion. So these appropriate wavelengths are there coming from the sun, and they produce. Now briefly, this is the geometry. The solar radiation is coming from the sun at an angle like this. So as it passes through the atmosphere, its intensity will diminish. The intensity can be taken as I infinity above the atmosphere, top of the atmosphere. As it comes down, intensity decreases at a given height h, or corresponding slant range s, intensity is high, and this angle between the solar direction of the solar radiation and the zenith direction here, this is defined as the solar zenith angle. So this is the geometry. So when the radiation comes like this, its intensity diminishes at this rate, that is di by ds is equal to minus I. It will be proportional to the available intensity. It is proportional to the number n of the absorbing molecules. So that proportionality constant is the sigma, which is called the absorption cross section. So the di by ds is equal to I minus I sigma n. The negative sign shows the intensity decreases as it comes closer to the atmosphere. Now, after absorbing this energy from the solar radiation, there is a efficiency factor eta, which decides whether it will produce a ion-electron pair or not. So the probability that absorbed radiation will ionize the atom is the ionization efficiency eta, and that decides the rate of ionization or rate of production of ion-electron pairs represented by Q, which is equal to eta multiplied by this sigma n I, that is the energy. So now we do some mathematical jugglery with all this, and apply some geometrical relation that the ds is equal to dh into secant chi, and then some concept that in the total columnar density in the atmosphere from a given height up to the top, that is integral n dh, is equal to the density there multiplied by the scale height over there. So by putting all these things and then making this integral, we can write an equation like this, that I is equal I upon I infinity is equal to exponential minus sigma n h secant chi, or this factor is written as a constant tau, that is called the optical depth of the atmosphere. That decides up to how much depth a particular radiation can penetrate, and at that depth, its intensity becomes insignificant. So now we assume the atmosphere is exponential, that is, density varies with respect to height in as exponential minus h by h. Putting this also into the substituting for n from that, we can finally write an equation Q, that is the rate of ion production, is equal to some maximum value into exponential 1 minus z minus e raised to minus z secant chi. So this is the celebrated Chapman's production function. Here Z is a measure of height, but it is made a dimensionless quantity by taking h minus h0 upon h, capital H in this case, h0 is in reference height. So this is the Chapman's production function, which shows that the production rate Q is a function of the reduced height Z as well as the solar zenith angle chi. So this graph shows each graph is for a different value of the solar zenith angle, varying from 0 to about 80 degrees. And this is the reduced height Z. So with respect to height, the production rate varies like this. They normalize the production rate with respect to that maximum. So everything is normalized. Y-axis and x-axis are normalized. So you get a maximum value at some particular height. And so below that, there's a sort of a parabolic type of variation. And then above that production peak, the production decreases. So there is a production profile, this is called, that is variation with respect to height. So the lower part of the profile is very much dependent upon the solar zenith angle. That comes out from that mathematical equation. But when you go to higher heights, the effect of solar zenith angle is not very significant. So that is why all the curves merge towards a single curve at higher heights. And another point note here is, you see in the early morning, the sun is almost at the horizon. Solar zenith angle is 90 degrees, 80 degrees like that. So at that time, the production starts at a higher height. As the sun moves, as we move toward the noon, the sun is coming closer to the zenith, and therefore the solar zenith angle is decreasing, and exactly at noon it will become 0. So at that time, the production peak comes down to lower heights. So the ionosphere production starts at higher heights. As the day progresses, it comes to lower and lower heights. So all these properties are actually observed, and they are very well represented by the Chapman's production function. Now, it is not only ionization by photons or photoionization, but also energetic charged particles can produce this kind of ionization. This is particularly important at high latitudes, where the solar radiation intensity is very small, but the energetic charged particles from cosmic rays and other sources, they can easily be guided to the polar regions by the magnetic field geometry. And so we get their energetic electrons in the energy range of a few hundred kilo electron volts. And depending upon their energy, they can produce ionosphere production or at different heights, even as low as 60 to 70 kilometers. Similarly, the energetic photons, for example, when the sun has a disturbed condition to solar flare, sometimes proton flares occur, and then very highly energetic protons are coming from the sun, and their energies are in the range of MeV. These are all in different values of MeV. And then different energies produce ionization at different heights. So the most energetic particle, 300 MeV or more, they can produce even at about 20-30 kilometer altitude ionization. So this is the role of energetic particles in producing ionization. Now we will quickly conclude in the next 1 or 2 slides. Once the ionization is produced by any of these processes, it does not remain indefinitely like that. It undergoes some further loss processes or loss reactions. And one such loss reaction is what is called recombination. That is, for example, a positive ion produced in the process can recombine with a free electron and get back to its neutral state. This way, the free electron and ion are lost. So this is a loss process. The rate of this process will be equal to proportional to available number of the X plus or positive ions, available number of electrons, which is represented here by N. and therefore it is equal to some constant alpha into product of these, or alpha into n square. And here we write n square because we said ionosphere is a plasma. One of the basic conditions which a plasma should obey is that the number of positive charge and negative charge should be equal, so that it is having bulk charge neutrality. So therefore the x plus should be equal to E. So therefore we can write this as alpha n square. Since the loss rate is proportional to n square, it is called a square law loss rate. So, so if this is the kind of loss rate, then we can establish a balance between production and loss, which is called photochemical equilibrium. Then the rate of change of electron density should be equal to production minus loss. And when equilibrium is attained, the dN by dt should be 0, or the Q will be equal to alpha n square, or electron density n will be under root of Q upon alpha. We have expression for Q from Chapman's production function, and alpha is a constant. So we can from that write that the electron density, number density of electrons, n is equal to some maximum value in the exponential half into 1 minus z minus e raised to minus z secant. So this is taken from Chapman's function. The half comes because of the under root. So a layer, ionospheric layer in which the electron density varies in this fashion according to this equation is known as an alpha Chapman layer. Similarly, another loss process is attachment, and in which a free electron can get attached to a neutral molecule and it can become a negative ion. So it is no more useful for radio wave propagation, or because it is no more a free electron. So in that case, the loss rate will be given by Q is equal to another constant beta into n. That case, the electron density n will be given by this formula, and layer which obeys this is called the beta Chapman layer. There is also a third loss process which is called transport or dynamical process, in which the electrodynamical forces acting on the ionization can lift it from its point of origin to some other region, or it can help diffusing it away from the production source, and therefore these also are important loss mechanisms. Finally, a combination of all these processes will decide the net electron concentration that you get in the ionosphere. So I conclude this talk here. In this presentation, materials from scientific research papers, books, and websites have been used. I am thankful to all the authors from whom I have taken